Hi everyone, welcome to your lesson on water quality. So we're going to be talking a lot about water quality, and then we're going to be able to connect it to an actual water quality study of Dairy Creek Branch, which is a little branch off of Little Sugar Creek, which is really close here to school. It's right outside of the bus lot. So we're going to see what the health of that body of water is based on all of the different things you're going to learn about in today's lesson. So the health of any water system is determined by the balance between three things, and it's between the physical, the chemical, and the biological variables. So some of the physical variables include temperature of the water, turbidity, which you'll learn about in a second. It's how cloudy the water is, and water movement, how fast does it flow. And when we go down to the Little Sugar Creek branch, we're going to be looking at each of these things, and we're going to test them to be able to actually determine the health of that body of water. In addition to physical variables are chemical variables, and these include how much dissolved oxygen is in the water and other gases, as well as pH of the water, so how acidic is the water, nitrates, and salinity, how salty is it. Both natural and man-made forces, which are biological forces, are constantly changing all of these different variables. So, couple things going on here. Let's start on the top. So on the top we see N, P, and K. And we just finished our lesson on our cycle on chemistry. And we know that N stands for nitrogen, P potassium, or P phosphorus, and K potassium. So each of these things are used in different fertilizers for lawns. And when you have an excess of fertilizers, whenever it runs, it leads to runoff. And it contaminates not only the groundwater, but it also runs off into bodies of water. And what happens is the fertilizers that you put on your lawns or in your gardens, they actually fertilize the water and increase growth of algae. And when you have an increase of algae, it shades out other plants. And when it shades out other plants, you have a decrease in the amount of dissolved oxygen in the water because that algae uses up all of the oxygen in the water. And so there isn't any more oxygen left over for the fish, and so all the animals in the water start to die. So, dissolved oxygen is a really good thing. We need dissolved oxygen in our bodies of water because all of the living organisms in the water need that oxygen in the water to survive. When you have algae in the water, the algae takes all of the oxygen away from the water, and so then there's not any left for the fish and other organisms. Okay. So dissolved oxygen, a good thing. Fertilizers in our water, not a good thing, because they take away dissolved oxygen because they help algae grow. Okay, so then look at the bottom left, you see turbidity. The very clear glass of water, that's low turbidity, and the super cloudy one is high turbidity. So cloudy water, obviously, is not super healthy compared to non-cloudy water for different organisms to be able to survive. The one on the right, the colorful range, is the range of tolerance for dissolved oxygen in fish. So less than 3 parts per million is too low for fish populations. Let's see, if we go all the way up to 9 parts per million, 9 parts per million supports abundant fish populations. So basically what you notice here is that the higher you get with dissolved oxygen, the more fish that can survive in that body of water. So again, dissolved oxygen is a good thing. You want to have it. The pH scale. So pH is another variable that's measured with the chemical variables. And if you look at the left side, as you go up towards 0, it's increasing acidity. And as you go down towards 14, it is increasing alkalinity. So if you picture this on a number line and you have 0 all the way up to 14, 0 to 0 is the most acidic that it gets, and 14 is the most alkaline that it gets. You like to think of alkalinity as like really soapy things, and acidic things like lemon juice, battery acid is more acidic than lemon juice. And then notice off to the right, you see the purple acid rain. Acid rain is between battery acid and just above vinegar. So adult fish start to die when it is around 3.5 to 4, which is what vinegar, how acidic vinegar is. The normal range for rain is between 4.5 to, between 5 and 6.5 is the normal range for fish. Normal range of precipitation, rather. Normal range of stream water is between about 5.8 and about 7.8. So 7 is on the pH scale, 7 is known as neutral. So 7 is really good. 7 is ideal for any body of water because it's not too acidic and it's also not too basic. Basic is another word for alkalinity. So you say something's acidic or something's basic. Okay, so water quality, so physical, biological, and chemical, these are all monitored by water quality standards that outline the Water Quality Pollution Control Program. And these are, any water quality standards are mandated and regulated by local, regional, and federal agencies. So standards outline the goals for a body of water by identifying its uses. So is this body of water going to be used for drinking water? Is it going to be used for recreation, for fishing, etc.? And then establishing how to protect those uses and establishing provisions to protect and preserve the water bodies in the long term. So because the water quality of a given water body is so closely linked to the surrounding environment, because when it rains, there's runoff. If you have impervious surfaces, impervious means water cannot soak through it, like concrete, parking lots. Well, whatever's on those parking lots is going to run off into the water body. And gasoline, oil, any kind of pollutants will run off into the body of water. So there's different sources of pollution. There's called point and non-point sources. And point source pollution means you can figure out exactly where it comes from. It comes from a single source. Great example of point source pollution is a pipe leaking from a factory. You can see it, you know exactly where in the factory it's leaking from. Whereas non-point source pollution is when a single source of pollution can't be identified. You cannot easily tell where it came from. An example is stormwater runoff. So the parking lot example I just said, where you have lots of different pollutants in a parking lot all running off into different places in a body of water. You can't tell exactly where it came from. So here's some other examples of point and non-point. So you can see the big smokestacks. You can see the pollution. You can actually point to it. Whereas non-point, agricultural is a very good example because agriculture in large quantities can produce a lot of pollution that can eventually make its way to the waterways. However, you cannot pinpoint exactly the exact place that the agricultural pollution came from necessarily. Same with urban non-point sources. Think about a city and think about how much pollution there is in a city. You can't often tell when you see a chemical spill, for example, where the chemical spill came from. You can't often tell when you see just trash, basic trash. You can't tell where the trash came from. All right, drinking water. So freshwater systems are really of concern because they are the source of most of the potable water consumed by humans. Potable water is water that we can drink. So water that's safe to drink is potable, and we have learned about potable water from camp. So oftentimes at camp, we'll see potable water and non-potable water. Potable water is the water that we had in our spigots at each of our campsites. In contrast to safe water should not be used for drinking, but can be used for bathing or cleaning. And in the United States, the Environmental Protection Agency, otherwise known as the EPA, sets maximum levels for the 90 most commonly occurring contaminants that we would see in water. So we are very, very lucky to have the Environmental Protection Agency because we are able to monitor so many different kinds of contaminants that are in our water. Our water is definitely contaminated with lots of different things. However, we have levels. We know because of the EPA how much our bodies can handle as humans of different types of contaminants. Without that, we would have our drinking water would be much more unsafe than it is. Clear water does not necessarily mean clean water, and that's really important because clear water may have odorless, tasteless, and colorless contaminants that are really harmful. Water must be tested for specific contaminants such as bacteria, nitrates, arsenic, and other harmful contaminants. Natural supplies of potable water are very limited and do not exist in big quantities to meet human needs. So because of this, humans have developed water treatments that process water so that it can be used for a particular purpose. So you guys are going to do a really great web quest on wastewater treatment and how drinking water becomes treated, but here are the basic steps so you can look back to this once you do your web quest. So first of all, the water's collected, and then it goes through what's called coagulation. And during that process, lime and alum are added to the water. And when you add those two things, it causes particulates or big clumps to form. Next, the water is shaken to form even larger clumps. So like the little clumps that form, they all stick together and make bigger clumps, and those are called flocks. During the sedimentation process, the water stands for approximately 24 hours, which allows those big clumps to settle to the bottom. Then the water's filtered, disinfected, usually with chlorine, and it's aerated. The substances removed from the drinking water treatment process include the suspended solids, bacteria, algae, viruses, fungi, minerals, and lots of chemical pollutants. So without this drinking water treatment process, we would have suspended solids, bacteria, algae, viruses, fungi, minerals, and lots of pollutants in our water, which would make it unsafe for us to drink. So here's a picture of the process that I just described. So up at the top left-ish, you have intake, so that's water collection. And then you have lime and alum, which makes it clump up. Then you have coagulation, which is where it clumps up into bigger pieces called flocks. Then sedimentation, where all the sediments settle to the bottom. And then water is filtered, chlorine is added, and it's stored. Then from storage, it's distributed to our homes and our schools and everywhere else that you see that you have access to clean drinking